Right, this video is on the formation of ions. In this video, we'll be talking about ions, specifically cations and anions, and the definition of those, and how they are going to play an important role in the discussion of chemistry from here on out. Okay, so in a previous lesson, we just learned about the octet rule. We learned that oct means 8, and the octet rule says that atoms are stable when they acquire or when they already have 8 valence electrons. And so also in a prior lesson, we have learned what valence electrons are. They're the outermost electrons in an atom. If you're not a valence electron, you're a core electron. But for our purposes, it's valence that we are really concerned with. We learned the almost cheat way to count valence electrons. And that is basically, it goes with the group across the table. So all group 1 atoms have 1 valence, group 2 has 2. And transition metals in the center kind of don't follow this pattern, so we skip them for now. And then we go 3, 4, 5, 6, 7, ending with 8. There's only one exception to this whole rule, and that is helium, who resides here. And helium only has 2 valence electrons. Okay, so that's valence electrons in the octet rule, and again, that was previously discussed in a prior lecture. Okay, so we said at the end of that lecture that the goal, and this was a big deal, is for atoms to acquire 8 valence electrons. Okay, we also said the way they're going to do that is they're either going to gain or lose electrons so that they have a total of 8. Okay, and this is the topic of today's discussion in terms of, well, how do they gain or lose electrons, and what does that look like when that happens? Okay, so the first thing we're going to talk about is something called the formation of an anion, and it's okay that you don't know what that word is yet, and that will be discussed in just a minute. Okay, so we're going to talk about fluorine. The fluorine atom. I'm even going to draw the picture. Say here's the nucleus. Here's the first energy level. Remember, it can hold 2 electrons. Here's the second energy level. It can hold 8 electrons. And I'll go ahead and put the third on. Okay, so if we're talking about the fluorine atom has 9 protons in the nucleus, and it has 9 total electrons. Okay, so I'll go ahead and draw that. Remember, 2 electrons on the first level and 7 electrons on the second level. Okay, so that gives me 7 valence electrons, right? Remember, 7 valence, 2 core, 9 total, 7 valence, 1, 2, 3, 4, 5, 6, 7 matches with my prediction that fluorine resides here and should have 7 valence electrons. Okay, so now remember, I'm calling this a fluorine atom, and the word atom here is very appropriate because the total charge of this atom is 0. It's got 9 positive protons, 9 negative electrons, giving me a 0 charge. Okay, no charge, and thus the term atom is appropriate. Remember, atoms have no charge. So from here, remember, back up here, here's the new goal. The goal is for atoms to acquire 8 valence electrons. Well, look at fluorine. Fluorine has 7. It's so close to having 8. And to get to 8, fluorine only needs 1 more electron. So let's pretend that we find an electron somewhere and we give it to fluorine. So what has now happened is fluorine still has 9 protons. See, I didn't change the number of protons in the nucleus. Remember, I can't do that. If I change the protons, that changes this atom from fluorine, and that's not allowed. I can't do it. But I did change my electrons. I went from 9 total electrons. I gave it 1 more. So now we have 10 electrons. And you can even count if you don't believe me. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons in my picture. this becomes, it might seem like it becomes problematic, because if you look at this thing is no longer neutral. If I take positive 9 for 9 protons and a negative 10, right? Why negative? Well, because electrons are negative. If I add those two together, it gives me an overall charge of -1. And all of a sudden, this thing now has a charge. This thing is now no longer an atom. Okay, the word atom here is no good, and it's no good because this thing has a charge. And remember, atoms don't have charges. So if fluorine now has a charge, I can't call this the fluorine atom. It doesn't make sense. I need a new word. And so my first new word of the day is the word ion, okay, which is just okay, I always say it's an atom with a charge. That doesn't make a whole lot of sense. So let's say, what should we say? We'll say something, this is a bad definition. Something with a charge. Can be positive or negative. Okay, so in this case, fluorine is now an ion. And the way we would write this is fluorine with its charge of -1 as a superscript, or like an exponent, okay? And that's denoting its charge. So as soon as I see that charge, I know this thing is an ion. Okay, so the other deal here is that it's a specific type of ion, and that's because it has a negative charge. And the specific type of ion is called an anion. And an anion is just a negatively charged ion. Okay, so F-1 is an anion because it's negative, but it's also an ion because it has a charge. So let's add in a picture of the periodic table. Oh, we'll just go back up here. Is there enough room? Yes. Okay, so there's enough room. So what happened to fluorine is that fluorine with 7 valence electrons gained an electron and magically had 8 valence electrons. Fluorine is now acting like neon. It didn't become neon, it's just acting like neon with 8 valence electrons. But now fluorine has acquired, let me get rid of that arrow. Fluorine has acquired a charge of -1. It gained an electron. I bet you can't guess what chlorine, bromine, and iodine also do on their quest to acquire an octet of electrons. Well, they all behave just like fluorine, and they all gain an electron. And notice, if they all gain an electron, they all act like a noble gas who has 8 valence electrons. So again, just like valence electrons had this pattern, so do these charges. So without drawing all these pictures, let's talk about oxygen, who's right next to fluorine. Well, oxygen has 6 valence, and so for oxygen, gaining 1 doesn't really help out, because gaining 1 puts oxygen acting like fluorine. But gaining 2, and watch, gain 1, gain 2, all of a sudden oxygen has an octet. So in this case, oxygen's going to acquire a charge of -2. So you would write it like O minus 2. So oxygen acquires a charge of -2. So does sulfur, who's underneath oxygen, and so on and so forth. Following the same pattern, nitrogen has 5 valence. It would need to gain 3. Gain 1 acts like oxygen, gains 2 acts like fluorine, gains 3 acts like neon. Ding, 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 everything's good. So nitrogen acquires a charge of -3. This is often confusing for students because they think gaining, and I should have a positive, but see, electrons are negative. So when we talk about gaining electrons, we're really talking about gaining negative charges, and that's sometimes tricky. I often refer to these ones as the gainers. Why? Well, because they gain electrons, okay? Everybody on the right-hand side is a gainer, and they gain, I shouldn't say everybody, most, and they gain electrons. They gain electrons, acquire negative charges, and are referred to as anions, okay? So just like we learned this pattern for valence electrons, this charge pattern is very helpful to us as we progress through this study. Okay, so since we've talked about the ones on the right-hand side now, and I've called them the gainers, we need to talk about the elements on the left-hand side. So I'm going down to my next heading, and let's start with sodium. And I'm going to draw the picture, and I know the picture might seem kind of redundant here, but I think it's helpful. So first energy level, second energy level, and third energy level. Okay, so again, the sodium atom, well, has 11 positive protons in the nucleus and has 11 electrons that are negative, total charge of 0. And thus the word atom here is appropriate. So if I draw it, 2 electrons in the first level, 8 electrons in the second level, and 1 electron in the third, giving me a total of 11 electrons. 1 valence, there it is, and 10 core. And again, 1 valence for sodium. If I scroll up to the top, here's where sodium resides on the table, and 1 valence electron makes sense. Okay. So, from here, the issue in this case is that sodium has only 1 valence electron. Where did I write that before? Over here. Okay. So with 1 valence electron, remember the total is to get to 8. So simple math tells us that sodium would need to acquire 7 valence electrons, right? 1 valence plus 7 new ones would give me 8. That's an awful lot of electrons. So while it's theoretically possible that sodium could gain 7, that doesn't happen. It's too difficult. What instead happens is sodium loses an electron. And sometimes, again, this is confusing because we think, well, if sodium loses 1 valence electron, then it must have 0 valence electrons. But that's not true at all, and that's why I drew the picture. So watch. If sodium loses an electron, it loses it from the third energy level, meaning the one I drew the arrow to, this one. Oops. So if sodium loses an electron, I go from, having 11 positive protons, but I've lost an electron. So I go to having 10 electrons, right? Remember I started with 11. And I get a charge of positive 1. Again, you might say, but doesn't that give sodium 0 valence? No, not at all, because now what are the valence electrons? Are the valence electrons in level 2, because that is now my outer energy level. And if you count 2, 3, 4, 5, 6, 7, and 8, sodium does in fact have 8 valence electrons. So chemistry is an interesting class where, in this case, I just taught you that 1 minus 1 somehow secretly gives me 8. So sometimes the math's a little funky, but it's only because my valence electron, my outer energy level backed down from being level 3 to being level 2. So because sodium acquired a positive charge, the word atom is no longer useful here. The word ion is useful. I would write it like this. Okay, and so ion because it has a charge, but not an anion, that's negative. The word here is cation, and it's said just like that, cation. And a cation is a positive charge. I teach my students, being kind of silly, that it's easy to remember that a cation is positive. Get it? Positive. Yeah, I know. I spelled it incorrectly, but it's supposed to make you remember. So cations are positive, and they involve losing electrons. So again, we sometimes think losing it should be negative, but see, if you think math class for a minute, we're losing negative charges, and that's like adding a positive, right? So anyway, if I go all the way up to the top, so what we've now learned is, let me change my color here. Sodium loses 1 electron and acts like neon. See, it totally acts like neon. Sodium has 11, and so when it loses 1, it backtracks all the way over to here and acts like neon, and that's what we want. That's the goal, to act like a noble gas. So sodium and lithium and potassium, they all do the same thing. They all lose an electron and acquire a positive 1 charge. Magnesium and beryllium and calcium, they aren't interested in losing only 1. They're interested in losing both their valence electrons. And when they do that, they acquire a positive 2 charge. And then the last one is boron's group. Boron and aluminum, they have 3 valence. They're interested in losing 3, and they become positive 3, a charge of positive 3. So these ones are called the losers because they lose electrons. Okay, now notice we've left somebody out of the picture. We've left out carbon's group. Okay, and you might say, well, is that because carbon has 4 valence and could as easily gain 4 as it could lose 4, right? Which puts it right in the middle. That's not exactly the real reason. The real reason is that carbon doesn't play this game of gaining and losing electrons. It does something completely different, which is a topic for another day. This seems to be my tagline here, but see, it's all connected. There's always another piece to the puzzle. So, what have we learned? That everybody wants 8 valence electrons, that they're either going to gain or lose electrons to accomplish that, and when they do, they become ions, which means they have charges, and it's important to keep track of those charges. So let's do one little example, and let's talk about, the barium plus 2 ion. And we want to know protons, electrons, and neutrons. Okay, so this is kind of the true test to summarize what we have learned in this lecture. So how many protons does the barium plus 2 ion have? Well, it's barium. So I go to the table and I look up the atomic number, and the atomic number is 56. So barium has 56 protons. Done. How many electrons? Well, if this was just regular barium, right? Just regular barium atom, it would have 56. But it doesn't have 56 because it has a charge. So what we should know is that that positive 2 means it has lost 2 electrons. So 56 minus 2 should give me 54. I want to show you that there's a way to check this, because see, some of you may have said 58. You may have said it gained 2 electrons, but watch, you can always check. If you know the charge of a proton is positive, then that means this example would have 56 positive charges. And if you know the charge of an electron is negative, then in this example that I'm doing right now, this would have negative 54 charges, right? And if you add those 2 numbers up, guess what you get? You get a positive 2, which matches the charge. So you can always double check if you're unsure. If you think you gained instead of lost, you can check. And then notice the protons and the electrons aren't equal. That means atom is not the right word. The right word is ion. And then, of course, neutrons, same old, atomic mass minus protons. So the atomic mass for barium is 137 minus 56, and that leaves me with, 81? Yeah, 81 neutrons in the nucleus